In the second elastic potential energy example, we have a spring of a known spring constant, 800 newtons per meter, that is hung from the ceiling. We don't know the resting length, we don't know the final length, but we know that an 8 kilogram mass has been placed at the end of that spring, and that spring has stretched to whatever that final length happens to be, even though we are not aware of it. The question asks how much elastic potential energy is stored in that spring once that 8 kilogram mass has stretched it to some unknown final length. Now, this is a slightly more difficult problem. If we try and take a look using just the elastic potential energy equation, we will find that we immediately run into a problem. Because while we know the K value, we don't know how far the spring has been displaced. We don't even know the initial and final positions of that spring. So we couldn't even subtract them to find out. So while it seems like a dead end, don't ever forget that when it comes to elastic bodies such as springs, Hooke's law is always a useful tool. So if I apply Hooke's law in this situation, if we draw a free body diagram, we recognize that the force of gravity pulling down on that 8 kilogram mass is 78.48. It's the mass times 9.81. And because that mass is just hanging there, we've hung that mass and it's stationary, there is no acceleration. So those forces must be equal. Therefore, when you hang a mass on a spring and it's perfectly balanced, then the spring force is equal to gravity. So in this case, we can use the gravitational force and the fact that there's no acceleration to realize that the spring must also be pulling upwards with 78.48 newtons. Once I know the spring force and I'm given the K value, now I can use Hooke's law, as I've used below. The force, 78.48, equals the spring constant 800 times the displacement of that spring. Dividing both sides by 800 gets me my displacement of 0.098 meters. Now, I don't know the initial length of that spring, and I still don't know the final length, but I know that whatever the difference between those 2 points are must be 0.098. Now I have all the information that I need, and I can quite simply plug that into the elastic potential energy equation found at the top. 1/2 the spring constant, which is 800, times the displacement, which we found using Hooke's law to be 0.098. If I square just the displacement, and then I find the product of those, I will see that 3.84 joules of elastic potential energy are stored in that spring simply by hanging that 8 kilogram mass. You'll find if you run into dead ends with these types of elastic potential energy problems, don't forget about Hooke's law. It will probably get you out of a jam more times than you can count.